It's a great pleasure to introduce you Yilong Zhang from Purdue University. That's going to speak us about correspondence between elliptic-elliptic surface and K3 surface. Please, Yilong.
Thank you for the introduction. Also, this my honor to put the speaker here. Thank you for giving me the opportunity. Because this is the last talk, so thanks the organizer again for organizing this. Okay. I guess I can make this talk concise and short. And so if you have any questions, just speak up, and I can answer all of them interactive. So the story still begin in the 100 years ago, and that's just one zero. And Professor Greer was introduced on Thursday, and so I found a photo of that is online, and it's one of the earliest photo I can find. So hopefully it looks more friendly than the photo we saw on Thursday. So this one theory say that every algebraic everyone passes on the algebraic surface is coming from algebraic curve. So this comes from the paper in the 1924. And its original proof is using the normal functions. And I still remember that there was graduate students being reached this curve, and it's presenting this proof of the Shioda-Inose theorem would be my oral exam. Alright, so that's just try to understand this Shioda-Inose theorem in a particular case. Let's try to understand it, what it say on the product two elliptic curves. So if you're in the product two elliptic curves, it's topologically you have just uniforms, product of four circles. So the topologically is it exists, but if you use the complex structures, and you start to see different Hodge classes. What that is one theorem is actually tells you that if you're moving your complex structures, you actually see the different PR rank. So what does happen? So well, we have to understand how this E1 and E2 are related. So first of all, if they are not geometrically related, since they are not isogenies, and you only have two classes. You have the E1 plus a point, and a point plus E2, and for sure that everybody has that curve class question. CM, roughly speaking, is that you can look at the elliptic curve as oceans of length lattice in the complex band. If your lattice point somehow define a number field, or in the sense that you have the self and the morphism, you by multiplying some complex numbers, and then you call that CM curve. In other words, CM means that your elliptic curves have extra self and morphism, other than identity or modification line. So okay, so then so in some cases your PR rank can increase. It really depends on if you have isogeny, meaning that you have a map between E1 and E2, and or you have a CM structure that you have the extra self and morphism, and these lead to the more algebraic classes. And So what we can summarize is that so if E1 and E2 are similar in the sense of a Hodge theory, and if they have extra algebraic curves on the pie. So now let's just think a little bit for what happens to with two Hodge factors. So if you want to study Hodge classes on the product of two surfaces, and we should study two Hodge classes. So let's work with the algebraic surface. And we want to look at the middle dimensional homology of this. So by Kuhn's decomposition, we know that there are a few pieces. We know that you can take H0, H4, and H4, H0, and H1, H3, and H3, and so H1. And the final piece is probably most interesting is the H2, H2. So again, it's very similar to the elliptic curve case that you have a point on the surface, and which gives you here in a surface point. As a point, you give you here. And sometimes you may consider non-simply connected surface. You certainly have contributions in here, but if we assume that it's simply connected, and then there is no contribution on these terms. And finally, the only contributions you're looking at is H2 and H2, meaning that you are looking at the weight to Hodge factor on both sides and consider that product. And because that your Hodge factors we then decompose the over rational numbers, the algebraic part, which is now a very group, and it's orthogonal complement, which is what they call trancedental Hodge structures. So it turned out that to study the two classes on the product of surfaces, and it suffices to consider the tensor power of the neural summary and the trancendental lattices. If you do as tensor product, it's just the harm. So you sort of the neural summary match to neural summary and transcendental match to transcendental, and they don't map to each other. And so because this is a usability. So it turns out that the interesting piece is actually looking for the comparison match between transcendental lattices. If there is a such map, non-trivial is certainly again something interesting. Otherwise, there's no. So what is predicted from the Hodge conjecture is that this move is a Hodge structure, and it must come from geometry. So what does it mean come from geometry? It means that you should have somehow you should find an object surface representing this map. So in the sense that what I call it roof diagram, and this looks like a roof. It means that you have a new object surface on the top, and it's going to dominate two sides. And when you consider pull back and push forward on transcendental Hodge factors, and then you actually get the original focus. So what is pull back, push forward? And so pull back is really just pulling back differential forms from the manifold to manifold. And when you push forward, you sort of thinking that you push forward as an operator. You're thinking that is you push forward homological cycles, and so your push forward is push forward your intervals of your forwarding the homologic cycle to the downstairs. So that's what we call it the loop diagram. And so in other words, it's going to the Hodge conjecture for this particular process on the product surface, we should find some such item. Yeah, question. No, it's in general not graph. That's the point. So if it's graph of a function, and then it's give you this correspondence. It's give you such a loop where maybe S3 equal to S1. But in general, this is you actually have the correspondence, what is called correspondence, meaning that your S3 map to 2 to 1 or 3 to 1 to one side and another function to 1 to the other side. So in general, that's the picture for the elliptic curves is sort of misleading. Maybe we should think about it going up and going down, and that's the most general case. Any other questions? Okay, so let's just think about the simplest case, which is a complexly complicated to understand, which is for the K3 surface cases. The K3 surface cases, it has interesting Hodge structures, and so it's H21. Sorry, H20 is one-dimensional, and what is transcendental is that you just subtract off the Picard rank, and that's counting the Hodge numbers of the transcendental lattice. And in particular, it's really small. So, what is in the literature called the Hodge isometry? It is the following. So suppose that you have two K3 surfaces, and the Hodge isometry, it means that you have a morphism of a Hodge structure of the transcendental Hodge structure from x1 to x2 as isomorphism of Hodge structure. And then you can consider the intersection pairing. This is a topological format where you have the punctured pairing of each two. You use the punctured pairing of the transcendental part, that's the pairing. And so it asks you to preserve the form. So let's say V1 pairing with V2. It has to be preserved. That's the notion of Hodge isometry. And so you can work for different coefficients. If you work with the integral coefficients, it's quite rigid. For the large Picard rank, there is a result by decoding and seeing that you actually integral Hodge isometry can easily determine that K3 surface. You don't have to be very. If you consider rational Hodge isometry, there is actually economics. So you have a very large room to study this isometry problem. And so what is has been studied is that in the historically is that rational Hodge isometry within K3 surfaces is algebraic, meaning that you always have this loop diagram for K3 surfaces, and as long as you require this morphism of transcendental as in preserving the intersection pairing. This was originally started with Kai in the 80s, where he first proved the cases where the rank is very large, and then he proved it a bit by decoding. And finally, in the 6 years ago, it was completely true in by Ustin. Ustin is a student of Kummer. So our motivation is to say, what can we say about other algebraic surfaces? So imagine what is SC? Oh yeah, that's a good question. So S3 in this case is they are trying to consider this fully retired constant. Your K3 surface sort of has a partner And in the sense that you can study these models of sheets, if you correct the character, that is also two-dimensional. So it's another K3 surface. And this loop diagrams come from some universal sheet. And the algebraic cycle come from in chain classes. It is not that explicit what the S3 is, but from the this correspondence is coming from there.
But when you take real guide transport, it's awful S3 real guide transport. This one shift.
Yeah, I mean, inside S1 times S2, you have a bundle. You take the chain class of the bundle.
You take each other in English.
Exactly. Maybe you take C2 and then it's a product and that's very important.
But S3 doesn't need to be K3 or
No, in general, it's not K3. So if it's K3, then you almost have like a movie on, so you have more. It's in general, S3 could have a very large zero, that's a difficult part. It's part one. In general, part one. So our question is to try to understand this algebraic cycle problems for elliptic surface. So what is the elliptic surface? So elliptic surface is that you have some algebraic surface in a map to a curve. Channel fiber is a torus. Is an elliptic curve. So that's a elliptic surface. And the simple example is mentioned in the Hertz column. You just take a pencil of the cubic curves in P2, and its base locus is in 9 points. Roll it up, and it's project to the P1. The general fiber is the application of your cubic curves, and that's giving you the first example for elliptic surface. And this elliptic surface is rational, so it doesn't have interesting structures. But also one interesting thing is that in general, this have 12 singular fibers. And why is 12 singular fibers? It was actually explained the Simpson policy on Monday, and he sort of explained why the discriminant of the cubic is 12. It's really you have the degree of dual right of cubic surface is 12. It is from there. And there is one invariant for elliptic surface. Associated is what we call a fundamental line model. So fundamental line model, roughly speaking, it measures how much your elliptic vibration is twisted. So, in this case, the rationally this surface is twisted by 1, so it's an integral invariance. So the way to think about it is that you can even work with this topologically. You can compute these numbers just by computing the topological Euler characteristic. So here, I go there is that what is true that if you work with elliptic surfaces, and assume that your fiber-wise doesn't have exactly one curve. And then what is true is that this topological Euler characteristic is always divisible by 12. So if you just divide by 12, and that number is the degree of this one line model. So that's just to compute what is the Euler characteristic of this. So because that we have so X is a rational elliptic surface, and we can remove 12 fibers and compute its topological Euler characteristic, and plus 12 times the Euler characteristic of this nodal fiber. And because if I remove the nodal fiber, and it's going to be a fiber bundle. So the fiber bundle, I have the product formula. So it's Euler characteristic on the fiber times the Euler characteristic of the base, which is P1 minus 12 points. But on the basic topology, we know that for torus, its Euler characteristic is 0. So this goes away. And it's an exercise to show that if you get one nodal point, and its Euler characteristic is 1. So that's why this is tau times 1 is tau, and it's divisible tau, and it's on the line always will be 1. So we can think about that. This D is sort of think that is D equal is topological minimum in that sense. Okay, so then let's try to construct on surface this interesting Hodge structure, which is the K3 surface. So how to construct the elliptic vibrations on K3 surfaces? In Hertz's talk, what he explained to us is that if you have two rational surface and glue along a fiber, you try to deform it, and you double the singular fiber, so you get a K3. But in this case, we prefer to consider phase change. So how does phase change work? So you start on this rational surface, and you take the degree 2 to 1 power of phase, and then you go back to bracket. So topologically, how do you think about what is phase change? So this is a so imagine that you have a sphere. The sphere is the base where you characterize the elliptic vibrations. So I have this vibration over the sphere. Now I take the north pole and the south pole, and I cut this north pole and south pole along the path. And also I take my pocket of elliptic vibrations over this K1, and also I cut another line for the second one. And I'm trying to glue them one together. So if you, for example, suppose your north pole and south pole doesn't have a single fiber, it's a smooth fiber, you're looking at a smooth fiber, and then this guy is still a smooth vibration. And sort of by computing this topological characteristic, then you can show that it's 24. So it turns out that the degree of this fundamental animal is 2. And so actually this is the proof that this is K3 surface. Because in general, this is the what is true is that you are just computing the genus of base and plus the degree minus 1. And in this case, the genus base is 0 and the D is 2, so it is 2. And so in general, so you can consider the elliptic vibrations for with two invariants. One invariant is a base genus of base degree curves. Base curves. And second invariant is this topological case. Again, so this formula for the Hodge number H20 is given like this. So in our research, we only work with the surface looks like a K3, like from Hodge theory. So we want this to be 1, and if we want this to be 1, the only possibility is that you consider 0, 2, which is the K3 case, or this is 1, 1, which is over a genus 1 curve. And so that's going to come to what we call the
previous slide.
Okay.
No
Well, by this move. So I'm saying that I assume that the north pole and south pole does not have it is a smooth fiber. In other words, the precise way is that your branch point is a smooth fiber, and then it will be. So our surface we are interested to study is called elliptic-elliptic surface. Meaning that our genus of base is genus 1. And degree is also equal to 1, so it's we have to think about its minimal because it has our singular fibers in general. And so topologically, you can think about it as torus vibration over torus, but it's not a product. So here is some just properties of these surfaces. So first of all, and it is no longer K3 surface, it's polarization 1. And because the phase is a genus 1 curve, is not simply connected. So here I want to say that there is a very interesting book written by Professor Morgan and Friedman, and studying this topology of elliptic surface, and that's where I actually learned how to shoot that. But it is not true. So the book is called a smooth fundamental and convex surface. So the model space, if you count the parameters correctly, you find it's 10-dimensional. And I just mentioned its Hodge factor actually looks very similar to the K3 surface because it has only one forms. And now let's think about what is going to be the Hodge structure. The Hodge structure is rather, we said, is polarized Hodge structure, meaning that it's just a fixed section and a fixed fiber. And so that's the elliptic surface. You always have this two curves. And you take the complement of it, and that's going to be a polarized Hodge structure. So with Hodge number 1, 10, and 1. And so in that case, so your period domain and periodic space is very likely K3-type period domain. And so it's also a 10-dimensional. And the period map is from this 10-dimensional organized space to the some 10-dimensional period space. And where this gamma will be the orthogonal specific intersection pairing exponential event.
What do you mean by K3-type?
Which part, son?
Hodge number is different from K3. What do you mean by
K3-type? It means that 1 something 1.
you know, H10 is 1.
Each Q0 is 1, and
and H10 is
exactly, yeah. So that's the point making it different. So here we only look at the period map for H2. Exactly, we forget about H1. H1 is actually to the I didn't mention that. So H1 of this elliptic surface is actually the same as the H1 of the base, which is just that 2. So you have a 2-dimensional invariant cycles downstairs, and that's the section giving the cycles downstairs. So if we only care about this period map for H2, and you can ask, does it satisfy, for example, infinitesimal already? And this is precisely just asking that if the period map is dominant, because we are working with some n-dimensional model size, n-dimensional period space. It's very similar to the history case. So this is a result originally proved by the 3 authors, Philip Engel, Constantine Rail, and Rail are in the 2 years ago. And last year we did a different proof. And our proof is rather just to construct a elliptic explicit surface and then compute its tangent map. We show the tangent map is the maximum rank, and then it must be dominant. This is a picture of what the surface we can start to practice. It's one of the surfaces with maximum deferred numbers here. And so you actually should still think about it as a targeting environment in the sense that the 3 of them apply to this 3 gun, and 6 of them apply to this 6 gun, and the last 3 of them apply to this 3 gun. That's sort of the picture. Okay, so this talk is trying to compare the Hodge theory between the elliptic surface and the K3 surface. So the idea is that the H2, if you think about H2 number, is 1 tau 1, and the K3 surface, the Hodge number is 128 1. So in the middle H11 is different by H. And you would think, well, how do you need this missing H? One possibility is that you just take a lattice polarization of the K3. You start to assume that you are looking at the K3 surface with large integral number. But it needs to contain the DA configurations. So we assume that the elliptic surface for the K3 side actually contains an EA fiber. An EA fiber is sort of is very related to the Aiken diagram of the Yilong Zhang pH, and it's at this shape. And if you look at this closely, it actually has 9 components instead of 8 components. So that is because that you need to add the very last component to make the following section area being 0 instead of -2. And so our polarizations for this surface is that you take a fiber, you take a section, and then you take the 8 components, which are these one time section, and then you have 8 technology curves. And they are going to spend some sublattice of your neuron subregion. And that part of the data is fixed. You just take the orthogonal complement, and that's sort of the primitive homology where so we call it lattice polarized history. So it turned out that if you consider this pure map or lattice polarized K3, you actually land in the same period domain. And then you ask what is going to happen for the pure map of K3 side. It turns out you still have a polarization theorem. Classical polarization theorem, if you think that you have a polarized by an ample line bundle, you have this polarization theorem. But it turned out that the Loga actually show that you have a lattice polarized. So if you're marking your K3 by some lattice in the subregion, you still have this polarization. So meaning that the first period that is the tomb is going to be finite in one. And this polarization on the K3 side is going to be at least 1 to 1. So it means that we can, for each elliptic surface, you actually have a unique the K3, and we use this EA polarization, this EA vibration corresponds to it. So that's the picture we are looking at. So here is come to the problems we are going to study. So we start on the elliptic surface, and then we call the Y the associated K3, they have the same image. And by this polarization, you actually have unique. Now, the natural question asking on the Hodge conjecture is that can you show that this correspondence on the trancedental Hodge factor is algebraic? Another way to put that, can you find this morphism on the Hodge structure geometrically in terms of loop diagram, and which you want to look for this S3 Hodge. One can even ask something more like the Muslim, can you say anything about rational Hodge isometry between elliptic surface and free surface? So if you forget about anything, just think about how do you relate to surfaces. It's kind of not that obvious because on one side your topology has non-trivial H1, so it is not simply connected. K3 has trivial H1. It's simply connected. So in general, it's not that easy to consider what is the geometric map between each other. So the way we're trying to construct this so-called roof diagram is to try to think one step further. We're sort of how do I come up with this S3 on top and like preserving the pullback of forms. So we're rather thinking that can you have some opposite roof diagram like if the two surfaces map to something common, and also it's preserved for multiple forms, and then you put back together, and then you just make fiber product, and that is the roof diagram. So let me write it down here. So we want to look for something like this. Let me call it the T1. The roof diagram is saying that you pull back push 4, give you the isometry of structure. But the precise condition is we are looking for is just that you are pulling back homomorphic 2 forms on one side, you pull back homomorphic 2 forms on the other side. And they should agree up to some scalar. Lambda is some number in C. And this is the condition where we're trying to look at. And in general, let's say this S3, suppose it only have one or more forms, and then this condition is for but in general, this is not true. So whatever the surface you can write down for this comparison, and I guarantee that you actually have a very large Hodge number. In general, you actually have the 2-0 form is usually very large number. So how do you construct something on the top where you pull back and moving this one-dimensional subspace, they actually coincide. So this is in general not easy to construct. What we think about is that we're thinking that what we call it a V diagram. So it looks like V. You can match something in common, and this guy has some homomorphic 2 form. And then you can put that like here, and on the fiber product, they should agree. So in other words, if you can find what we call a V diagram, and then you actually have this the roof diagram. So you solve this out basically.
What kind of properties you expect?
Finite dimensional map. Yeah, that's what we're trying to. So it's in our case, we are going to consider double cover of K3 surface. But this double cover is not a regular morphism, it is a rational morphism. And, so a rational morphism is now a factor for morphism forms. That's all right. So now let's move a little bit to the geometry side. Let's just think backwards. Forget about this character problem we're going to solve. Just think about can you explicitly construct any K3 surface with a elliptic vibration with an E fiber? Right? How do you even write down such a thing? So it's sort of compounded amazing work by this Shioda and Inose in the 70s. So what did they show is that if you start on the Kummer surface associated with two elliptic curves, and then what is going on is that you have evolution maps on the elliptic curves, and which has a 16 bit form. So let's just do that. You have let's say D1 plus B2, and you have the evolution operation on that. So this is going to be let's say x1 x2 maps to negative x1 negative x2. So So if the x2 equal negative x2 means that in the porous, and that is one of the fixed points. So then you actually get the projection second coordinate. You are seeing that the elliptic curve is acted by this involution and with 4 fixed points. And so that you actually get 4 horizontal curves. And similarly, say if you look at the conditions x1, it's going to be a fixed point. And if you get the other direction vertical for dashing curves. And the places where they meet is 16 points. That's the total fixed points for both coordinates. And that means that you have A1 singularities and one coordinate. You have to picture that sort of infinite and then what Shioda-Inose do is that, okay, you look at this configuration of the vector curves. You find an EA configuration here. And it's given by the vector color. And it's not very clear by the EA, but I guarantee you write it down. And which curve intersect which curve is actually EA. And there's a general theorem for K3 surface that it should be any effective divisor whose self-intersection is 0. And then there is the elliptic vibration whose one of the fiber is going to be that the effective divisor. And then this gives you the proof that you actually have a EH sphere fiber in the vibration. So in the example where you take the product of 2 same elliptic curves. So this is a CM curve, where E0, I know that it's the elliptic curve with J dimensional. And what they show is that you have this E8 fiber, you also have this E6 fiber and E4 fiber, and it's sort of the most singular vibration you can consider. And if you add up this number of curves in the correct way, and it's going to be handy. So it's mathematical paradigm in this case. So what they can consider is that you consider some rational double cover of this surface. Branch and fiber which is not E2, which is not E8. You branch along the other 2 singular fibers, and they get another elliptic K3 surface. And in the literature called Shioda-Inose structure is saying that they have without comparing the trancedental structure of the Abelian surface with this double cover K3 surface. So this diagram looks very similar to the V diagram, and actually that's it has similar ideas with us. Now I want to just give a rational geometry interpretation of what is Shioda-Inose structure. So now let's just pause for a second and really think about what this double cover of a K3 surface issue. So you say, wait a second. So if I just start on some elliptic vibration of the K3 surface, if I take the general double cover branch at 2 smooth fibers, and it's like you have taken 2 spheres and cutting along the line between the north pole and south pole and move them together, and I guarantee you that this singular fiber is going to double. And if the singular fibers get doubled, its topology is going to complexity is going to increase. So that is going to say that the wrong thing to do is that if you choose general double cover, you actually get something which is not K3, because it has for the age singular fibers counted basis of knowledge base, and it's Hodge number is 3, and it's not K3. So that's a non-example. It's not a wrong thing. So what it's going to do in the Shioda-Inose is that you want to carefully choose your branch point. So you want to actually choose your north pole and south pole to be some singular fiber And this fiber has to be fat enough so that it is going to somehow decrease the topological complexity of the surface with base change. So it turns out that this is going to be a condition that you want to base change at some of this non-reduced fiber, which has type D and D. So what we find is that some criterion in general that how do you compute this degree of the line model capturing the topological complexity based on the base change. So it turns out that the expected degree is just the degree downstairs multiply the degree of the covering of this curve. And that's assuming that you are looking at the general base points. But suppose your base point is in special positions, and you have to somehow subtract some local contribution and what we call impact. And this is precisely related to the semi-stable reduction of your this arithmetic genus one curves. And it is on here. And in the other case, we sort of in application, we only look at double cover. So it means that you want to take a double cover and the branch has some non-reduced fibers. And every time you do this, and you get a defect by one. Okay, so now our purpose is to construct an elliptic surface from double cover of K3, similar to what Shioda-Inose does. And to compute this, so first of all, we need to base curve to be some genus one curve. And how to construct a genus one curve from the branch cover of T1? Well, we know that it has to be, you take 4 branch points. So the first base we have to consider base change is that you want to take the double cover of T1 and the 4 branch points. And secondly, let's just compute this defect. The defect is telling you that my elliptic surface should have this minimum twist. It's the degree of when the line model should be 1. So I want this to be equal to 1. And but if you take the general base change double cover of K3, the degree equals 2, and the degree of base change is 2. It's 4. So we need to subtract off by 3, and 3 is the defect, and which corresponds to the 3 single fibers on your original image. So this is some very bad fiber, and the 3 very bad fiber. So this is your K3, and when you do the base change, you actually get the elliptic over here. Okay, so as an example is that if you start from this, what is in the literature it's actually called the most algebraic K3 surface, which has an elliptic fibration with the E8 fiber, with E6 fiber and E4 fibers. So here I'm also using the Roman numerals with the original Polaris classification notation. You take the 2-to-1 double cover and a branch and 4 points. So here the 3 points is at the base of the single fibers. You have a very last point, and it's a 3 point, and you can choose freely in it's a smooth fiber. Your base change and branch at these 4 fibers, and upstairs, and it's going to turn this E8 fiber to some E6 fiber, and this E6 fiber to this 4 fiber, and this E4 fiber actually becomes smooth. And you have a very last, very smooth point. If you compute the Euler characteristic, it's actually add up to 12. So it's another proof that you have the elliptic surfaces. So anyway, so you actually constructed, by this way, you constructed a one parametric family of surfaces over elliptic curves, which actually have a constant Hodge. Just because that's the Hodge theory, you can come back on the transmission part, is already rigidified by the surface downstairs. You have a one parameter family of the this elliptic surface with trancedental Hodge structure. At least over rationally, is completely determined by the surface downstairs.
So you mean like some close point whatever choose the same construction.
You got the same contact.
So even if it is it coincides with one.
Oh, coincide is another story. So coincide you get something else. You don't want the last point to coincide with any.
Okay, but like so if you have not so much construction, you should allow it to coincide.
Coincide is you want to study the limiting mix structure. So the way you construct a smooth elliptic surfaces, your full branch point has to be disjoint. If you are moving one point together, your base becomes an auto curve. Your base becomes an auto curve, and if you want to singularize this, and then your base becomes P1, right? So you normalize it becomes P1. So actually, this is how we find the limiting structure of this one parameter family. It's related to what you point out. It's a point. All right. So now this is our main theorem. So this is I actually mentioned that it's joint work with Arapura and Arapura and Greer. So this work is not posted on our cabinet, but we hope to have it very soon. So what we proved is that if you start from an elliptic surfaces, arising from this double cover of a K3 surface with three non-linear fibers. And then you can solve this correspondence problem. So then any rational Hodge isometry to the other side of the K3 surface is algebraic. So the way we proved it is sort of already explained in the previous slide, is that we construct this so-called V diagram, and the basis is the K3 surface. And the V diagram gives a Hodge isometry to elliptic surface and this double cover of the K3 surface constructed by Shioda-Inose. And then the boosting theorem and it tells you that any rational Hodge isometry with K3 surface is already algebraic. This is what and then we have to check any case. Sort of the algebraic cycle we are constructing is really the fiber product of this V diagram. And so that's our result. And as I have a little more time, I want to just say something different as how I just mentioned. So this is something like we actually didn't completely understand, so I didn't include in the slides, which is exactly to construct this degeneration. So I like the very last base point, branch point of line. So now I think I have a P1. So I have some singular fibers. Let's say this is the singular fibers. And I'm considering this branch out cover. And branch out these fibers and the very last fiber. So your base change is going to you have this elliptic curve in this way. And then you can allow this last base point to collide with any one of the three singular fibers. And if you do that, you actually get a normal curve. And when you normalize it, you actually get a P1. So it's sort of telling you if you construct this family of elliptic surface, what is turned out is that first the H2 variation of structure is just constant. Secondly, it's if you look at it's H1, it is infinite order. But by infinite order, I mean this monarchy operators along one of the generation consider. So why is infinite order? So you are degenerating an order curve to the monarchies. So in particular, your band of surface is not constant surface. But the H2 is somehow constant. And then you ask what is the leading mix function factor? So the compute sort of leading mix function factor. And the leading mix function factor on H2 it is actually pure. Just because that if you think about I'm allowing the one of the last mix point to align with the branch point. When you normalize, you are putting this 2 points on branch to the original family. Now you're over a P1 base. And over P1 base, your other two fibers it is going to carry over, which is let's say it's here. So other 2 points is still base change. So it's the 4 star 4, and this going to smooth fiber. But this collided base points is going to tell you that you have to undo the base change. In other words, you have to go back to itself. So you actually get a 2 copy of this. This thing is a K3 surface. So this K3 surface supports your pure unit means function. So we run into the problem is that when we compute the limiting K3 surface, 2 of them are same. One of them is not the same as the last one. So we have a 3 linked K3, which is 2 of them the same, and it is not included in the last one. So one interesting phenomenon which I come to Christian is that it is already talking that if you look at the time sequence, it is not exact or integer. So that's sort of the implication of this phenomenon. So if you actually look at this critical model of K3 surface, if you have annual monogeny, it's going to tell you that after some finite power, you can find a smooth model. But this is not the case here. Because you have non-trivial monogeny for H1, so it tells you can never find a smooth limit. But somehow the limit surface and the sort of puts the H1 like on this on here, and the H2 is sort of supported on the limiting K3 surface. They have the same rational structure, but interval structure. I'll just come to the very last one, right? And saying that to repeat our results, we solved this correspondence problem sort of only for, we submitted it's only for very special elliptic surfaces. This surfaces fails infinitesimal already, and correspondingly, they have a constant period point. So these are not general. So you can ask the same question about related problems or general elliptic surface. And I guarantee you that you cannot find a V diagram. So you really have to find a V diagram, but we have no idea what the various outcome. So that's a question that one can ask. And the second question is that this period map, the period map, we sort of using this method, this is some n-dimensional space, and it is the finite one. So we find some positive dimensional fiber. in our results coming from the base chain of K3. But we wonder, how do you characterize all the possible dimensional fiber of this grid map? Are they all come from the base chain of K3 as we constructing? That's something we are trying to do, but we haven't got there yet. The last one is that it is already known that it fails the genetic already, meaning that it's not 1-to-1, it's 2-to-1. And how do you compute the degree of this map? And sort of that's some